All right. My next video is about model fitting. So for the sake of an example, I'm going to give you some simple example, right? So suppose that we work with the data of Earth population that I downloaded somewhere. So in million of people. Now, what we need to do first, we need to come up with a differential equation that kind of autonomous differential equation that kind of reasonably explains the Earth population. So the growth rate of the Earth population should be some function in terms of the population itself. And what we want is we want it so that when we solve our system, well, our differential equation and plot the solution, it's going to more or less pass through these points as close as possible. Now, here is our model. So it is a pretty reasonable model. Huh? So we are saying that dy dt, so dy dt is the growth rate of the Earth population, is proportional to the population itself raised to some power alpha. So this alpha is some positive number. So what the exponent alpha should be here, we don't know. So we will try to find a value of alpha so that the model more or less fits the data. Now, the point here is that for every combination of some specific values for k alpha and y by 0, y naught, we can solve it and see how well the solution fits the data. So here is an example. So for the given values of k alpha and y naught, so we can solve it and see, okay, this is not a very good fit. And it is probably pretty clear what we should do, right? So we see that the actual Earth population kind of grows much faster, so which probably means that we should take a bigger value of alpha so that it kind of grows faster. At the same time, in the beginning, so before 19th century or so, before at least before 15th century or so, the growth rate is kind of slower, so which probably means that our k should be smaller, right? So we want something like this. And here is our next attempt. So now I made k smaller, but alpha bigger. And you see that now the fit is pretty decent, is much better. Well, it is important to understand that it is possible that for some combination of parameter values, the solution will approach infinity in finite time. Now, I made this presentation in R, but so here is what the error message looks like in R. So in Python, it's going to be a different error message. In MATLAB, it's going to be a different error message, but it will be an error message in any case. So you just need to know that if you have this error message, it probably means that the solution approaches infinity in finite time. Then, for the sake of this example, I used a simple model that can be solved explicitly, right? So because my equation is a separable equation, right? So I can separate the variables. So I can write that this is dy over y to the alpha equals k dt, integrate, well, and solve it. But in your project and in Rinaldi's paper, it is impossible to do that. There is no way to solve it explicitly. But it is possible to solve it approximately on a computer with very good precision, actually. So this is called numeric simulation. And the output of this looks like this. It is a list of values of the time for which you want to compute the dependent variable and the list of the corresponding values of the dependent variable. So in my case, I only have one dependent variable, so the Earth population, but you will probably say, I don't know, Rinaldi has 3, so Petrarch's emotion P, Laura's emotion L, and Petrarch's poetic inspiration Z. So there will be a table for P, L, and Z. So you will have 2 or 3. Now, to measure the quality of fit, we use the so-called error, or sometimes it is called cost, or a loss function. So in artificial intelligence, usually it is called a loss function. Well, basically this error or the cost of the loss, so this error function, so let me use the word error function, right? So it measures how much the simulated solution deviates from the data, right? And there could be different ways to define this error function, but the most common error function is the so-called mean squared error that you are probably familiar with if you learned some basics of linear regression in statistics. It is the same mean squared error as in statistics, right? So it means the following thing. So it means that if P is a vector of some specific values for K, alpha, and Y naught, then for every specific combination of K, alpha, and Y naught, we can approximately find Yp of t. So we can solve the corresponding system of equations, and we can find it approximately. And then at the given time moments for which we have observations of the historical Earth population, so we find Yp at those moments, and at the same time we know the actual population, Yi, at those moments. And then we take the squared error, well, the mean squared error. So, and it is quite clear that because the square is always positive, right? So this E of P is 0 if and only if our solution goes through all the observation points precisely. And the more it deviates from these points, the bigger is the error. Well, just to put it into some perspective, so these are our two solutions, solution 1 and solution 2. Well, I mean, combination of parameter values 1 and combination of parameter values 2, right? So, well, to be honest, I divided the actual mean squared error by 1 million to find this. So the actual error is the same thing times 1 million. But you see that the error of solution 1 is 10 times bigger than the error of solution 2. And you see, from the plot that the second solution is indeed much better than the first solution.